Welcome to the NVIC chapter of the HT32 MCU basic tutorial. There are 3 chapters in this tutorial, including the NVIC Introduction, the NVIC Function, and the relevant settings and applications. NVIC Introduction. NVIC, Nested Vectored Interrupt Controller, is a peripheral in ARM processors, primarily responsible for interrupt management and exception handling. To better understand interrupts and exceptions, refer to the diagram below. Assume the MCU is executing the main program from step 1 to step 6 marked in blue. During main program execution, if an event occurs, the main program flow is interrupted. This event could be an interrupt request, IRQ, triggered either by the core or peripherals. Upon receiving the IRQ, the MCU suspends the main program, interrupting its normal flow, and jumps to execute the interrupt service routine, ISR, marked in yellow. After executing the ISR, the MCU returns to the main program to continue execution. These events that disrupt normal program execution are categorized as either interrupts or exceptions. The key distinctions between interrupts and exceptions are summarized in the table below. Interrupts, sources generated by external MCU peripherals with configurable priority. For example, external button presses and data transfer completion events. Exceptions, sources originate from the processor core that typically have higher fixed priorities. For example, hardware faults. For the NVIC to properly execute an interrupt service routine, ISR, it must first fetch the handler address from the interrupt vector table. Next, we'll explore how interrupts, exceptions are processed. When a peripheral or the core triggers IRQ2, the program must transfer execution to ISR2. However, a problem arises: how does the system locate ISR2's entry point? Since ISR memory addresses are dynamically allocated, the solution involves consulting the interrupt vector table. The interrupt vector table contains the starting addresses of all ISRs. Returning to the previous example, the vector table lookup yields address 2 as ISR2's starting location, and the program will jump to the correct address 2 for execution. In simple terms, the interrupt vector table is a table that maintains the starting addresses of all ISRs. When an interrupt or exception occurs, the processor indexes into the interrupt vector table with the IRQ number to retrieve the associated ISR starting address, thus executing the correct interrupt handler. NVIC Function. The NVIC's primary functions are summarized as following: configurable interrupt priority, flexible interrupt management architecture, vector table relocation mechanism, supports low power mode, software reset capability. In general applications, MCUs typically handle multiple concurrent interrupts. However, some interrupts are mission-critical and require immediate execution upon triggering, such as emergency braking or alarm events. The NVIC can implement an interrupt priority management mechanism, ensuring high-priority interrupts are serviced first. Taking the Cortex-M3 as an example, interrupt priority is divided into 2 parts: preemptive priority and sub-priority. The preemptive priority determines interrupt nesting capability. When a higher priority IRQ occurs, it will preempt any currently executing lower priority ISR and immediately trigger its own ISR execution. For example, suppose the I2C interrupt is configured with higher preemptive priority than the EXTI, external interrupt. If an EXTI external interrupt occurs, the MCU will execute the EXTI ISR. If an I2C interrupt occurs during EXTI ISR execution, since the I2C has a higher priority, it will preempt the EXTI ISR, immediately executing the I2C ISR instead. After the I2C ISR has been executed, the MCU will return to the previously saved EXTI ISR and continue executing the remaining EXTI handler code. After EXTI ISR completion, returns control to the main program flow. This design ensures timely execution of high-priority IRQs, preventing interference with critical operations. For example, I2C transmissions require immediate processing to prevent transmission errors. Next, we examine sub-priority handling. When multiple IRQs share identical preemptive priority, they cannot preempt each other. Execution order is determined by sub-priority values. Higher sub-priority IRQs are serviced first, but cannot interrupt already executing ISR with the same preemptive priority. It is important to note that Cortex M0 Plus supports only preemptive priority and lacks sub-priority functionality. The NVIC can enable or disable specific IRQs. This ensures that the system only responds to required interrupts while preventing unnecessary IRQs from affecting system operation. The related APIs are as follows. NVIC_enable IRQ enables the specified IRQ. NVIC_disable IRQ disables the specified IRQ. NVIC_get enable IRQ checks whether the specified IRQ is enabled. When a new IRQ is triggered while the MCU is executing an IRQ with the same priority or higher priority, the new IRQ enters pending state. Pending IRQs are serviced only after current ISR completion. To better understand the behavior of pending, please refer to the example below. Suppose the main program receives an IRQN, and the main program is interrupted. Program execution jumps to ISRN handler. If IRQM occurs during ISRN execution, since the IRQM priority is not higher than IRQN's, IRQM will be latched in pending state. IRQM remains pending until ISRN completes execution, that the system will activate IRQM and execute. Finally, the program returns to the main program to continue execution once ISRM has finished. The IRQ pending status can be queried using NVIC_get pending IRQ. As previously mentioned, the interrupt vector table stores the starting addresses of ISRs corresponding to each IRQ. By default, the interrupt vector table is located at the starting address of the flash memory, which is usually address 0. For example, when IRQ2 is triggered, the system will query the interrupt vector table to find the starting address 02 corresponding to IRQ2 and jump to that address to execute the ISR. However, in certain application scenarios, such as firmware updates, the NVIC need to execute alternate ISR sets. This is achieved by reprogramming the vector table offset register, VTOR, to remap the vector table's base address, allowing the system to fetch ISR starting addresses from a new memory area. Suppose the vector table address relocate from flash address 0 to the address hex 20000000 in SRAM. The VTOR would be modified to SRAM. When the NVIC receives IRQ2 again, the system will recognize SRAM as the starting address of the vector table, look up the table and jump to the new ISR starting address, address RAM2, to execute. The NVIC supports 3 low-power configurations: Sleep Deep, Sleep on Exit and SEV on Pend. These configurations help the MCU enter power-saving modes under specific conditions and provide flexible ways to wake up the system according to the requirements. 1. Sleep Deep. If Sleep Deep is enabled and a WFI or WFE low-power instruction is executed, the MCU will enter the deep sleep mode. In the deep sleep mode, the MCU will shut down more peripherals to further reduce power consumption. 2. Sleep on exit. If sleep on exit is enabled, after the program is awakened by an IRQ and the ISR has been executed, the MCU will not return to the main program. Instead, it will directly enter a power-saving mode, remaining in power-saving state until awakened by the next IRQ. 3. SEV on pend. When entering low-power mode via WFE with SEV on pend enabled, the MCU can be awakened by any pending IRQ event even if the IRQ has not been enabled. In simple terms, SEV on pend expands system wake-up conditions as specified in the following table. When SEV on pend is 0, the MCU can only be awakened if the new IRQ priority is higher than the current executing IRQ priority. Otherwise, the MCU cannot be awakened. Additionally, if pry mask is set to 1, all interrupts are masked, the MCU cannot be awakened regardless of the IRQ priority. When SEV on pend is 1, the MCU can be awakened regardless of the priority of the new triggered IRQ and regardless of the pry mask setting. In addition to interrupt management, the NVIC provides system reset functionality through software triggers. This allows the program to trigger a system restart initiation via software, eliminating dependence on the external NRST, reset pin, hardware signal. Settings and applications. After understanding the main NVIC functions, the following will further explore how to configure and implement related functions. The following will explain priority configuration. Step 1. Setting the allocation ratio between preemption priority and sub-priority. The number of levels for preemption priority and sub-priority is not fixed but dynamically allocated. Taking Cortex-M3 as an example, preemption priority and sub-priority share a 4-bit configuration range. The allocation ratio is set via the NVIC_setPriority grouping API. The allocation results are shown in the following table. If priority group equals 3, all 4 bits are assigned to preemption priority, resulting in 16 levels, with a settable range of 0 to 15. If priority group equals 4, 3 bits are assigned to preemption priority, resulting in 8 levels, with a settable range of 0 to 7. 1 bit is assigned to the sub-priority, resulting in 2 levels, with a settable range of 0 to 1. This pattern continues. Different priority group values correspond to different allocation ratios between preemption priority and sub-priority. By inputting the parameter 4 in NVIC_setPriority grouping, it means the preemption priority can be set within the range of 0 to 7 and the sub-priority can be set within the range of 0 to 1. Supplementary note, the Cortex-M0 Plus does not support dynamic allocation. It has a fixed 2-bit preemption priority, with a settable range of 0 to 3, and no sub-priority. Step 2. Setting the priority for each IRQ. The smaller the priority number, the higher the priority. The highest priority that can be set is 0. The relevant APIs as follows. NVIC_setPriority sets the priority for a specific IRQ. NVIC_encode priority combines preemption priority and sub-priority into a single encoded value. Usage example. Call NVIC_setPriority to set the priority of the target IRQ. The first parameter is the target IRQ number and the second parameter is the priority number. Since the priority number is an encoded combination of preemption priority and sub-priority, NVIC_encode priority must be used to pack them. The 3 parameters of NVIC_encode priority in the usage example are as follows. Priority group. Set to 4. Preemption priority and sub-priority. Both set to 1, which represents the second highest priority. The following section describes how to trigger an IRQ pending via software. Typically, an IRQ pending status is triggered by external peripherals or the MCU core. However, the NVIC provides a mechanism that allows an IRQ to be manually set to the pending state through software. What happens to the IRQ after manually setting it pending? The following example explains how the IRQ state changes after manual pending. Call the NVIC_setPendingIRQ API to set the specified IRQN in the pending state. If there is no currently active IRQ or IRQN's priority is higher than the currently active IRQ, the IRQN state transitions from pending to active, its corresponding ISRN begins execution. Conversely, if the IRQN priority is not higher than the currently active IRQs, IRQN will remain in the pending state until the current ISR completes execution and will then be processed. The library provides multiple APIs to manage IRQ pending states. NVIC_setPendingIRQ sets the specified interrupt to the pending state. NVIC_setPendingSystemHandler sets the specified system exception to the pending state. NVIC_getPendingIRQ retrieves the pending status of the specified IRQ. NVIC_clearPendingIRQ clears the pending status of the specified IRQ. The final section will explain how to relocate the vector table. Vector table relocation can be achieved through the NVIC_setVectorTable API. The first parameter, NVIC_vectTable, specifies the memory for the vector table allocation, with options for either flash or RAM. The second parameter, NVIC_offset, specifies the memory offset from the vector table base address. Usage example: set the memory to flash and set the offset to hex 200. When using vector table relocation, pay attention to the following points. 1. Vector table content validation. When relocating the vector table, it is essential to ensure that the content of the vector table is correct. If the content is incorrect, the system may not be able to handle interrupts properly, and may even jump to an erroneous memory area to execute, causing a system crash. 2. Vector table address alignment requirements. Taking Cortex-M0 Plus and Cortex-M3 as examples, the vector table base address must satisfy 256-byte, hex 100, alignment. This means the starting address must be an integer multiple of 256, e.g., hex 100, hex 200, hex 300, etc. NVIC software reset function. As shown in the following APIs. NVIC_core reset. This function resets only the MCU core, while the state of the peripheral circuits is maintained. Additionally, Cortex-M0 Plus does not support this function. NVIC_system reset resets the entire MCU, including the core and all peripheral circuits. At the end of the tutorial, this is a list of NVIC APIs. The content includes the reference files, API name and description as well as the associated register name. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.